Welcome to our presentation on analyzing a real-world turbine. So in the team, we had Kayla Dombach, who wrote the code, Hannah Scharf, who revised and ensured the code ran smoothly, and me, Kevin Zheng, who clarified the code. And we all worked on making the presentation. For our objectives, we had to compute departure functions using the Peng-Robinson equation of state. We then had to compute work done and efficiency of an N2 turbine given in class. And then we had to update the code to fit a real-world turbine and analyze the data obtained.
Our code starts off by taking in the critical properties of nitrogen, as well as the inlet and outlet conditions of the nitrogen passing through the turbine. The code requires an equation of state in order to function. We started off using van der Waals, then Redlich-Kwong, and then finally the Peng-Robinson equation of state, as shown on the slide. With each new equation of state, the data generated became more accurate as more variables were introduced. The specific volume of the nitrogen was calculated for both the inlet and the outlet streams using the Peng-Robinson equation of state and fsolve in Python. Departure functions act as a way to determine the change in a thermodynamic property between a real state and an ideal state. The departure functions for enthalpy and entropy are pictured on the top right of the slide alongside the code that computed the enthalpy departure at each state. Partial derivatives of the equation of state were taken and plugged into the departure functions before solving at each state. And shown here is the departure function for entropy calculated at both states. The ideal changes in enthalpy and entropy were computed between states 1 and 2, and the total changes in enthalpy and entropy were then summed up using the departure functions as well as the ideal changes. By making the assumption that the work is equal to the negative change in enthalpy, the work of the turbine can be computed as shown in the first section of code on the slide. Additionally shown is the calculation of a new final temperature, assuming an isentropic process with the same inlet conditions and outlet pressure. This will be used to help calculate the efficiency of the turbine later on. Using the isentropic final temperature, we can then calculate the reversible work similarly to how it was done before. We can then divide the real work done by the turbine by the isentropic work to get the efficiency of the turbine, which we got to be 78.9%. This matches up nicely with the example that was done in class.
On this slide, you can see a diagram that shows what the turbine from the report we found looks like. This is a high-pressure steam turbine located in Rijeka, Croatia. As you can see, this turbine has one inlet stream and 3 outlet streams, which are indicated by the red arrows in the diagram. This steam turbine is analyzed through both the energy flow stream and isentropic method in the report. However, we will be focusing on just the isentropic method. Here, towards the top of the slide, you can see a table from the report that includes the temperature and pressure values we are using for our inlet and outlet parameters. The pink arrows on the right-hand side of the screen indicate the data we used for the inlet stream and the outlet streams. At the bottom left of the screen, you will see a table that shows the turbine power calculated in the report at 3 different turbine loads using the isentropic analysis method. In our analysis of this turbine, we will only be focusing on the power calculated for a 100% turbine load, which is indicated in the pink box. In order to calculate the work and efficiency of the real-world turbine in the report, we had to make some changes to our previous code. The critical properties were changed from nitrogen to water, and an additional outlet stream was added. This stream combines streams 3 and 4 in the real turbine because they both leave the turbine at the same conditions. The specific volume and departure function calculations did not change when updating the code to fit the turbine. The only difference is that there were 3 specific volume and departure function calculations rather than 2. This is due to the fact that we are analyzing a turbine with more streams. Additionally, the temperature variant heat capacity was changed from nitrogen to water. We calculated the work of the real-world turbine from the report in the same way we calculated our turbine work in our previous code. The turbine work we calculated was 257.5 megawatts, which is 20% higher than the work of 206.1 megawatts calculated in the report. The process of finding the isentropic final temperature did not change from the previous code. However, this time we calculated 2 different final temperatures rather than 1 to account for the additional outlet streams. After calculating these final isentropic temperatures, we calculated new isentropic enthalpies and compared them to the original enthalpies to determine a turbine efficiency of 97.05%, which you can see on this slide. This differs from the efficiency stated in the report at 100% load by 4.39%.
So comparing our results with the report, we had a 4.39% difference in efficiency and a 20% difference in work. This could be due to many reasons, but we narrowed it down to 3. Firstly, departure functions and equations of state are only models of real-life values, and they won't represent specific values completely accurately. Secondly, the assumption that W is equal to negative delta H may not be completely valid for the turbine, and frankly, it is beyond the scope of this course. Finally, our report states that the mass was lost through gland seals. This means that the turbine would produce less work, which could lead to the 20% difference in work.
Thank you for listening, and please make sure to comment and subscribe.